G'day guys, how are you going? This is the third time I've done this video on our Test 7 differentiations and applications of. Let's not get worried why it didn't work the last time, but hopefully this is third time lucky. So we did this test at the end of term 3 and students got it back either the end of term 3 or start of term 4. It was a good test, people did well, but lots of little things we can pick up. So hopefully going through the answers helps to build a little bit of understanding where maybe it wasn't. Here we go. First couple of questions were largely straightforward, but each question was testing a different thing. This was your simplest basic one. A power out the front, lower the power by 1. That's all we need to do. F dash of x, derivative of. No problems at all. 2 marks, easy marks. Over here, a little more difficult because we've got a fractional power, but it's the same idea. Power out the front, lower the power by 1. This here is the power out the front. Lower the power by 1, a little bit of tidy up. Notice the different notation, dy dx, it means exactly the same as f dash x. Should be able to interchange the notation. Whatever they give you, work with that. Don't go changing it to something else, work with what they give you. So let's have a look in question part C and part D. Part C here is a little different in the fact that the x value is on the bottom line. So we would really need to bring that to the top line to make it easier for us. So if you bring the power out the front, lower the power by 1, we get this. Lowering the power by 1 is this one. Remember, if you're at -2 and you lower the power by 1, then you're going to -3. A lot of students often will say, oh, that's -1. No, you actually raise the power by 1. This is lowering it by 1. Now the question right up the top said with positive indices. So what that means is that we need to change this, bring it back down to the bottom line to get this. Okay? Again, the notation follows through. 2 marks there. You would have got 1 if you did this. 2 marks back to here. This one, this is a good one, this next one. You could have done this a couple of different ways. This is probably the simplest way, but you could have done it a couple of different ways. You could have gone 2x squared plus 1 times 2x squared plus 1 times 2x squared plus 1. And then multiplied all of that out. It would have taken you a while. Not the way you want to do it. What I've done is use Pascal's triangle. If you're not sure about that, then look into that one. What have I done? It's the first thing raised to the power of this, and then it's 3 lots of this one raised to the power of 2, this one raised to the power of 1. See how those powers add to 3? Then it's 3 lots of the first one raised to a power of 1, the second one raised to the power of 2. Alright? See how as this power is decreasing, the second thing, the power is increasing. And the coefficients of 1, 3, 3 and 1, I got those from Pascal's triangle, or you could use your combinations as well to get that. It's really 3 choose 0, 3 choose 1, 3 choose 2, and 3 choose 3. Once I've got that, which sounds complicated, but it's not actually once you know what you're doing, I can tidy up and I get this, and now the differentiation part's easy. After that, it kind of falls out. The tricky stuff was expanding it out easily. The derivative was quite simple. Question number 2. Now I can't fit all of this on the screen at once, but let's see if we can just make it a little bit smaller. Nope. It's not going to work. So what I've done here is I've picked the key points on my original graph. And I've done some dashed lines down and I've written what I want them to become. Maximum turning point, because the gradient went steeper, 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 steepest, and then shallowed off again. So that's going to be a turning point and a maximum one. Over here is going to be a minimum turning point because it got the most steep, negative, down, there, and then shallowed back out. The zeros become x-intercepts. So I put all that information on, the plus, the minus, the 0, the dashed lines, and scroll it down. Now if you do that, it becomes relatively easy to draw because you're kind of just connecting the dots. So do this notation that I've done, do this. This is the way to see it. When we're doing the second derivative, it's really just the same thing again. We're just taking a new graph and moving it down to this next one. Now, exactly where this turning point is, or this one in terms of high and low on the graph doesn't matter. That doesn't matter, okay? Because you see on the f of x, or f dash of x, or f double dash of x, there's no scale on that. So we don't worry about that when we're drawing these sorts of things. It's the shape and the position of things relative to the x value that matters. Question number 3, good little one here, a couple of variables floating through in some sort of quartic equation. But I know there's a stationary point at 1, 4. Stationary point, that means the derivative is equal to 0, which is what I've done here. I've worked out the derivative, and I've let the derivative equal 0 when x equals 1. The stationary point is at 1, 4. So the x value of 1, think of that previous question, dashing it down, right? We'll have a 0 point on the gradient function. Okay, so that's why I've done this here. So therefore 0 must equal this thing with 1 inputted in, which is what I've done. Solve a equals minus 2. Once I've got a equals minus 2, I've got that guy there. I've just got to figure out b. Well, this point 1, 4, that is on the original graph, isn't it? That's on the original graph. So can't I just use this with a in there, minus 2 in there, and just know that it's going to equal this? Follow on through 5. Now, in these sorts of questions, if you came out with, I don't know, minus 7 over 9, you've probably made a mistake. They generally fall out pretty neatly. Maybe a half or a quarter in there, maybe, but generally they fall out with whole numbers. So if you kind of work your way through, some crazy number comes out, probably done it wrong, look again, leave it, move on. Use calculus to determine. So calculus must show some derivative going on here. The nature of the stationary point, minimum, maximum, horizontal point of inflection. Second derivative, at that point, x equals 1, came out with a positive number. So because the second derivative came out with a positive number, it's got to be a minimum, or concave up. If this was negative, it would be concave down. If this was 0, it could be horizontal point of inflection, minimum or maximum, and we'd need to do a bit more investigation either side to see which ones of those we had. In here, it was a minimum, that's all we needed. The exact coordinate of the other stationary points, of all other stationary points, first derivative, let it equal 0. That's going to give me all of the stationary points. Okay? Now, I did this, I factorised that. Be careful. Don't do this. If you divide through by x, or if you divide through by any variable, then that variable cannot equal 0. Because otherwise, you've divided by 0 and that's undefined. So this is not okay. Now the reason that will make this question you not get full marks for it is that by dividing through by x, I must then state that x cannot equal 0 to avoid that case of the fact it will be undefined. So if I say that x cannot equal 0, then you'll notice over here one of my solutions was x equals 0. So don't cancel down when you're solving things, factorise. Factorise means you don't lose your solutions. One of the solutions is going to be 4x equaling 0, or x equals 0, or this one equals 0. That's the difference of two squares, so you could have written x minus 1, x plus 1, and got your two answers, or move it over, take the square root of both sides, plus or minus. Okay? Now, one of those, the plus one, we already knew that from up above, so we didn't need to play around with that one. We just need to find the coordinate for x equals 0 and x equals minus 1, because it said all other stationary points. We already knew the one above, so you didn't need to do that. Okay, question number 4. The equation of the tangent of the curve. Now this was a bit generous. 5 marks, should have been 3. Should have been 3. So well, let's see. The tangent of the equation means that I need to expand and then differentiate. Expand and then differentiate. Once I've got the derivative or the gradient function, I'm going to put x equals 5 in and get the gradient at x equals 5. I then use my linear equation, put the gradient in, and use the whole point 5, 8 to figure out the C value. Now, in this question, I made a mistake here. I never went back and tidied this up. Have a look here. This will be 135. Move it over here, it'll become negative 135. So these two should be around the other way. This should be minus 127, and hence minus 127 there. I'll tidy that up in a moment. I never got back to tidy it up. Question number 5. D squared y dx squared is the second derivative. Okay, just a bit of fancy notation. Same as f double dash of x, same thing. Simplify where possible, writing your answer with positive indices. So if we're given this, we just need to take the derivative of each part twice. The first one's not really so bad. Power out the front, lower the power by 1. Do it again, power out the front, lower the power by 1. This one's a little trickier. So what I'd suggest you do is see that these things here are all equivalent. So x cubed and then the square root of it is the same as this, and then we can multiply the powers to get x to the power of 3 over 2. That makes it a little simpler. Okay? It's then in your regular kind of format for power out the front, lower the power by 1. So now that I know that, power out the front, lower the power by 1, show that I get this. You can see this. Here's the power out the front. Now 3 over 2 is 1.5. Lower the power by 1 is going to be 1/2. And then do that again. I mean, I put that in a different format so you can see what it would look like. But then to do the second derivative, it's power out the front. So the half comes out the front. And this would become a negative half. A negative half, because if I lower the power by 1 from 1/2, I go to negative 1/2, which means that that there goes to the bottom line. Okay, so that's our final answer there for that one, and that was the end of the non-calc section. Skipping straight along to the calc section, a little quicker here because I've shown you how we do a lot of this on the calculator. Find the coordinate of the point where the curve cuts the line. Y equals -1, that's a horizontal line, isn't it? Okay. And I've got y equals. So I just let that equal that, and then throw it on my calculator and solve. Answer comes out at -3. It did ask for the coordinate, but I already know y equals -1. So I already know the y value, -3, -1. Determine the gradient of the curve at this point. So we're talking at this point here. Well, that means I'm going to have to take the derivative of that one. What have I done here? Solve. I'm telling the calculator I want you to solve this for me. I want you to solve the value of the derivative. d dx is the derivative. Solve the value of the derivative when x equals -3. So it's going to do the derivative of this and then substitute in x -3. Answer came out at 6. If you're good with your calculator, 20 seconds and you're there on that one. Oops. Question number 7. Revenue, cost, profit type of question. Remember, revenue is the amount of money you're bringing in as a business owner. Cost is what you have to pay to get your product to the shop ready to sell. And then profit is the difference between the two. Now we've got some setup costs here of 1,000 as well. So the setup costs might be for, I don't know, hiring the hall, or maybe or the business premises. Maybe the cost of a repaint before you open. You're only going to have to do it once, but something you have to do. Show that this is our profit function. Well, revenue minus cost. Here's my revenue one. I just took that straight from above. Here's the cost function, and here's the fixed cost that I had to add on, or actually take away. Bit of number crunching, through I come. You wouldn't have got any marks to this last line because that's exactly what's over there. You needed to show where it came from. Next one, determine how many items need to be sold for the maximum profit. I'll just leave that there. Right, look through here. Look through here. This is the dominant power. X cubed is the highest power. It's the dominant power. It's a minus x cubed. That means it's going to look like this. All right? So when I'm talking about how many items need to be sold for the maximum profit, this first turning point is going to be the minimum. This one, the second one, is going to be the maximum. So solve the derivative of p of x equaling 0. Because solving the derivative equaling 0 is finding the turning point. So my calculator gave me 2 answers. I'm going to discard this one. That's the minimum one. I know that that corresponds with that point there. I want that one, which is that one. Now, really it says how many items. You can't sell, buy, etc. 18.16 items. So I'd round that to 18, but I allowed a decimal there. If you put 18.16, you've done what I wanted you to do. I paid that. But in the second part, I didn't allow decimals. Determine the maximum profit. Now I wanted you to recognise that I can only sell 18 of them. So while 18.16 gets me a bigger number, I can't sell 18.16 of an item. So therefore I had to go with 18, which was that. You notice 19 would be less, and if I rounded this down to 17, it would be less as well. Okay? So you would have got 18.16 here, not here. You would have lost a mark somewhere if you didn't do that. Part D, determine the marginal. As soon as you see marginal, you're looking at the derivative. The marginal profit, marginal cost, marginal revenue is when you say, okay, I'm at this point right here, what is the cost, profit or revenue for selling, buying or making one more item? It's kind of the, if I sell one more, do I make money? So the derivative gives you the instantaneous change. The derivative is the marginal profit. Here it is. I put 10 in and I get 400. So what does that mean? That means if I sell one more item, instead of selling 10, if I sell 11, that means that I make $400 more profit. If that value was a negative, that would tell you you're making less profit by selling more. I know that sounds a little odd. You're thinking, hang on, but I'm selling more. Well, yes, but your costs might increase substantially as well for selling more. Okay? So positive marginal profit, you're on good ground, you're making more money. Negative marginal profit, you're making less money by selling more. Question number 8, last one here. This was a good question, a lot of number crunching going on here. Total surface area of metal that we're using, a bit of information there about the length and width. Draw yourself a diagram. Diagram, easiest way to see what's going on. 2x and x, that's the double thing. H here is the height, that's going to fold up to make my box. Surface area, because that's what I was given here. Surface area, here's the 6 pieces of the shape. And then I just made a couple of substitutions. Instead of L, I wrote 2x. And a bit of number crunching, put the 48 in. And it's a bit of work, but we get there. We knew what we were getting to anyway, because that was in the question. So you knew when you'd got to where you needed to be. Next one then says, show the volume of the container. The volume of the container in terms of x. Well, volume is length by width by height, isn't it? And again, length we know is equal to 2x. And you just figured out up above right here what the height was in terms of x. So that goes there. Multiply it out, tidy it up, and we got there. Okay? A little bit easier here, but if you'd struggled above, you're probably going to struggle there. The last one then says use calculus to determine the maximum volume. The maximum volume of it. Therefore derivative turning point. V dash of x. So I'm taking the derivative to get here, letting it equal 0. Right? Once I've got that, I can get a couple of solutions. Now, because we're talking measurement, it's got to be a positive number, doesn't it? X, 2x, h, they've all got to be positive numbers. So I'm going to discard the minus 2 one, don't want that one, throw that away, I'm going to use the 2. I want to check that it's a maximum, second derivative became negative, therefore it's a maximum, right? Negative second derivative means it's one of these. Once I knew I was on the money here, I then take my 2, put it back into the original formula of volume. Bit of number crunching, 21 1/3 meters cubed. Don't forget your units on the end. A lot of work in this last question. Not an easy question, but if you got full marks for it, which was 10 marks, you were going to do pretty well on the test overall, I'd suggest. Hopefully this one helped you. Good luck, exams aren't far away. See you later, guys.